Hi, we propose an L1 minus L2 variant of Tubal nuclear norm for guaranteed tensor recovery. My name is Andong Wang. This is a joint work with Guo Xuzhou, Zhong Jin, and Qibin Zhao. In today's big data age, tensor data is almost everywhere. But in many applications, only a few noisy observations are available. So how to recover the true tensor from a few noisy observations? In this paper, we first formulate the observation model as follows. In this observation model, the observation yi comes from the inner product of the true tensor L star and a design tensor xi plus an additive noise ci, where the index I ranges from 1 to n, and we get n noisy observations yi of the true tensor L star. In order to recover the true tensor L star from the n noisy observations, the Tubal nuclear norm-based models were proposed. The Tubal nuclear norm, also known as TNN, is defined as the average nuclear norm of frontal slices after DFT. That is, for 3D tensor T, we first conduct one-dimensional discrete Fourier transform on all its tubes and get a new tensor. We call this new tensor the Fourier tensor and denote it by TLT. Then, the averaged nuclear norm of frontal slices of TLT in this way is defined to be the TNN. TNN is also equal to the scaled nuclear norm of the Fourier block diagonal matrix denoted by T bar. The Fourier block diagonal matrix is defined as the block diagonal matrix whose block diagonal submatrices comes from the frontal slices of the Fourier tensor. However, TN yields suboptimal performance due to the biased approximation of rank T bar. In this paper, we propose a tensor L1 minus L2 metric for tensor recovery. It is based on the L1 minus L2 metric, which is defined as the difference between the L1 norm and the L2 norm scaled with the parameter alpha. According to the level curves of the L1 norm and the L1 minus L2 metric, we can find that the L1 minus L2 metric is a tighter approximation of L0 norm than L1 norm. Motivated by this metric, we extend it to the tensor L1 minus L2 metric, which is defined as the rescaled L1 minus L2 metric of the singular values of T bar. Then it is expected to be a tighter approximation of rank T bar than TNN. With this new metric, we define the proposed estimator as the tensor L with the smallest tensor L1 minus L2 metric such that the noise level is lower than tau. The first problem is how well can we estimate the true tensor? We answer this problem by bounding the estimation error, which is the difference between the estimator L hat and the true tensor L star. Theorem 2 gives an upper bound on the estimation error in its Frobenius norm and tells us that under a certain tensor rip condition, we guarantee stable tensor recovery. Another question is how to solve the proposed model. We first derive a closed form solution with the proximality operator of the metric, and then add auxiliary variables for better decoupling and use ADMM. Specifically, the original problem is transformed to its equivalent form by adding auxiliary variables k and epsilon, and then solved with ADMM. We first conduct tensor compressive sensing and tensor compilation on synthetic data, where the proposed metric outperforms TNN. We also conduct image imprinting, in which the proposed metric-based model outperforms the competitors. So we can see that the proposed metric has promising performance in tensor recovery. Thank you.